Hello, it's my pleasure to welcome you to the revision of the Industrial Electronics N2 paper that was written July 2024, right? So without much further ado, let's quickly go into the questions. I will skip the instructions for the sake of my time and progress, but I do advise you that when you're in the exam, go through them to understand them. It's very, very important. Okay, question number one then was saying on mixed chapters. Draw and label the IEC symbol for each of the following electronic components. Okay, the varictor diode. By the way, the other name for the varictor diode is varicap. It's important also to know that. So the symbol, the adopted symbol is this one. That of a diode combined with a diode with a capacitor. Then of course it's variable. There is the arrow, right? Or we can also use this symbol as well. The other symbol that we can actually use. That of a diode, then we indicate the capacitor, right? There is the symbol, right? So varictor diode. These are the symbols that either of them you were okay if you had indicated that, right? Light emitting diode. The light emitting diode again is the symbol for the diode, right? The normal PN junction diode. Okay, then it's gonna be having, okay, so this is how it's gonna be looking like. Then there is it must emit light. There it is. These arrows indicating the emission of light, right? So the anode indicate the anode. As a matter of fact, even on them, the varictor diode was also okay to indicate the anode as well as the cathode. There is our light emitting diode symbol. Then the next one was the PN 1.3 PNP transistor, right? PNP transistor is one of the BJTs, the bipolar junction transistor that under discussion, the two of them, the NPN and the PNP. So oftentimes candidates tend to have a problem with distinguishing between the PNP and the NPN, especially on the symbol. So I always advise my students to do this. It makes it easier. You see, both of them, they look similar, but then the arrow for the PNP is pointing in. There it is. Okay. There is the PNP. The arrow is pointing inwards. Right. So there is the base, there is the collector, there is the emitter. This is our diagram. So how best can you know? You know that this is the PNP, right? For the NPN, it's not pointing inwards, it's pointing outwards. The same arrow here, it will be pointing outwards. So how best can you not make a mistake? For the PNP, you can say not pointing in, not pointing. You know that it's not pointing, it's pointing outwards. For the PNP, you say pointing in, pointing in. So you don't make a mistake. It's just a way of trying to remember. Right, so that's the PNP transistor for us, the symbol. Let's go to the light-dependent resistor. So for the light-dependent resistor, there is the symbol, right? Resistor. We have the symbol of the resistor. Then, of course, right, to indicate that it's a light-dependent. My circle there is a little bit poor. Let me try to indicate it nicely. Okay, there it is. 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 Right. Pardon my. Okay. So I'll try to indicate it nicely there. There it goes. Okay. Okay. There we go. Right. The arrows should be pointing inwards. They are the arrows pointing in. There is the arrows pointing inwards. Right. That's two arrows there pointing in. It's indicating the light-dependent resistor. Then we have also the thermistor, right? For the thermistor, this is the light-dependent resistor. Then the thermistor, it is like this. The resistor again, but remembering now this is a temperature dependent resistor. this temperature coefficient, right? So we have it. There it is. There is plus, there is minus, because it can be a positive temperature coefficient. It can also be a negative temperature coefficient, right? So these are the symbols. So I do advise that we go into the text, go through the symbols. As a matter of fact, as you go through each and every topic, make sure that the circuit symbols that are involved are understood. It's very, very important, right? Let's go quickly to question number 2 there, right? Question number 2 is saying use the diagram above and calculate the total resistance of the circuit, right? First things first, it's important to interpret how the circuit looks like. So I advise that we start here at the source, right? There is the positive, there is the negative, right? We follow the conventional flow of current. Current flows are from the positive to the negative. So if we try to follow it, let's follow the current that's flowing from the source. It's going through R1, which means R1 we experience the same current that is coming from the supply. Right? But when the current reaches this junction that I'm marking here, it will divide to mark I1 and I2 that we are seeing there, I1 and I2. Right, so I1 and I2 are as a result of the division that is occurred to our current from the supply. So let's label it as total current IT. Now, it must be known that that division of current marks a parallel circuit, because a parallel circuit, by simpler definition, it's simply a current divider circuit. Whenever current is divided, then we know that those resistors are in what? In parallel. So for that reason, we are saying all these resistors here, these ones, and all these resistors here, these ones, they are in parallel. The two groups, the two branches that we're having, they are in parallel, right? So it marks a parallel combination there, right? Apart from that, let's follow I1 as it goes up, right? I1 will flow through R2, but at the same time, it reaches this junction here. It further divides again the I1 on its own. It will divide some current going towards this direction, some current, which means R3 and R4 are in what? Are in parallel, the two of them. Let's proceed, right? So it, of course, it's going to recombine here back as it goes. Now, the same thing, let's follow I2. I2, when it reaches this point again, it's going to subdivide. Some of its current I2 will go through R5 and some will go through R6. It marks again another parallel combination. Then that's how our circuit looks like. So it means all these resistors that were in parallel, these ones, they are apparently also in series with R1 and R8. So here is my advice when you are now performing calculations on this. Start from the furthest point you feel or you think resistors are in parallel. You start minimizing or simplifying the circuit from there. So we can start here, this parallel combination here that we see. And we can call it our first parallel combination. Let us call it RP1. We can call it RP. We are RP1. Just to indicate that is one of the parallel combination that we are having. So those two are in parallel and there are two of them. So for two resistors that are in parallel, we can simply use the formula product over sum directly. 8 times 16 over 8 plus 16. It works only for two resistors that are in parallel, mind you. Right, so we multiply that quickly. 8 times 16 over 8 plus 16, that will give us 5.333, 3 decimal places there. Okay, ohms, which means that parallel combination here is 5.33. Now, this 5.33 that we have just gotten, what is it to the 4 ohm? To the 4 ohms. Right, that 5.33, apparently it is in series now with the 4 ohm. So we can therefore say 5.33, okay, 5.333 there, 5.33 plus 4. If we add, we are going to get 9.33 ohms. Right, so it means this branch, this whole branch here, it has an effective resistance of 9.33. We call it an effective resistance or an equivalent resistance. And from there, we go to this branch. We go to this branch, right? We are seeing again another parallel combination here. let us also calculate it. So we will call it RP2, that other parallel combination of what? Of the 6 ohm and the 12 ohm, mind you, the explanation that I was giving there. 8 times 12, sorry, over 6 times 12 over 6 plus 12. Why? Product over sum. So we just simplify that directly. What do we get? We get 4 ohms, right? That's 4 ohms there. Now that 4 ohms we have just determined here, the 4 ohm. What is it to this R7? Right, with R7, it is in series. Therefore, we are simply going to add. So we are considering R5 and R6. We are saying they're in parallel, just like as we did with R3 and R4, they're in parallel. So we then add their equivalent resistance 4 plus 4, and it's going to give us 8 ohms. So 8 ohms as it stands, it is now 8 ohms. It is the effective resistance of this whole branch here. So we have two resistances now. We have 2 resistances. The 9.33 we got there, and the 8 ohm we are getting here. Right. Now what's happening with these 2 resistances? These two, the 8 ohm and the 9.33. They are the ones that experience now the divided current I1 and I2. Therefore, the 2 of them, they are in what? In parallel. So they mark our third parallel combination that we see. So we will label it RP3. Right. RP3 now is for 9.33 and the 8 ohm. Right. So again, they are just 2. So product over sum again. 9.333 multiplied by 8 over 8 plus 9.33, or 9.333 plus 8. It's one and the same. Okay, so what do we get? We get 4.308 ohms to 3 decimal places again there. Right, so it means on our branch, on the whole branch that we have in this whole branch, this one, it's giving us 4.308 ohms. Right, now that 4.308 ohms that we've just gotten, what is it to R1 and to R8? It's now in series with both of them. Therefore, we can now use the 3 resistances. We now have this effective resistance plus R1 plus R8. They now mark our RT, the total resistance. So we now say RT is equals to the first one, which is 8, okay, 8 plus, okay, so let's just indicate it nicely there. Okay, so it's 8 plus 4.308 plus the other one, which is 15 ohms. So if we add them all, they are going to give us 27.308 ohms. That marks the total resistance of the circuit. That becomes now the total resistance of the circuit. So it's very important that it's helpful, should I say, that we start from the furthest point and we try to minimize our circuit. You are going now towards the source. That's our RT, the 27.308 ohms that we've just determined. Let's go to the next question. It was saying, calculate the total current flowing in the circuit. Total current flowing in the circuit. The total current using the supply. Now, if you notice, we do not have the supply VT. So where are we expected to find the total current from? Okay, so I'll try to clear off my screens that I just explained clearly there. Okay, here's what is happened. Here's what is happened. We have been given the current here, I2. We've been given the current I2. Now, we also even know the effective resistance of this whole branch, of this branch here. We now know it. We know, we have calculated it, and we got 8 ohms there. Right. So it means that if I am to calculate directly and say, what is the voltage of this branch? Why would I want the voltage of the branch? Because if I can find the voltage of that branch, I can use it to determine the current. I can actually manage to find the current. So what do? I will simply say, okay, VP2, remember we had said this branch here, it's R2. So we can call it a V2. since we have I2 also in that regard. So we will simply say V2 is equal to I2 multiplied by the resistance of the equivalent resistance of that branch, so which is 0.3 times what was the resistance there. It was 8. Remember, the 4 ohm plus the 4 ohm we got here using product over sum. So if we now multiply 0.3 multiplied by 8, that will give us 2.4 volts, right? So this is what we have. Now, the voltage that we just got apparently is also the voltage of the other branch across. Why? Because resistors in parallel have the same voltage, mind you, which means the voltage doesn't change. It is the same for all resistors that are in parallel. Right, so we take that advantage now to use that voltage to calculate I1. Why are we interested in I1? Because if we use I1 and I2, we add them, they are going to give us I total, the total current of the circuit. So it means I1 is now equal to V2 that we have determined divided by R of that particular branch, the total resistance, the effective resistance of that particular branch. So we are simply saying 2.4 divided by, remember, we had gotten 9.333 here. So we are saying 2.4 divided by 9.333, and we get a value that is 0.257 amperes. Right. So we now have current I1. We use I1 and I2 now to find I total. Why? Because we understand that I total is equals to I1 plus I2. Due to Kirchhoff's first law, the current law, it tells us that current entering a junction is equal to current leaving the junction, which means I total, which is coming from the supply, is equal to I1 plus I2 that are at the junction there. So it's possible we can do that to find I total. So it's going to be 0.257 plus 0.3, and we simply add that, and it's going to give us 0.557. That marks our total current amperes. Was this the only way we could have done it? No, it wasn't the only one. Remember, we have the current divider rule. The current divider rule says I1 is equal to R2 over R1 plus R2 multiplied by I total. That's what it says. Right. So we have I2 there, so we can use that. So for I2, it means it's going to be I2 is equal to R1 over R1 plus R2 multiplied by I total. Right. So going back to our junction, our I2 we have been given it's 0.3 amperes. So we can use that formula there to calculate total current, right? What then is going to be our R1? Our R1 shall apparently become this 9.33 that we got, and our R2 will become 8 ohms, the resistance of this, the effective resistance of this whole other branch. So using those two resistances, we can directly say, first, by making IT the subject here, how we can multiply by R1 plus R2 both sides, multiply by R1 plus R2, multiply here again by R1 plus R2, right, plus R2. So we end up having I2 multiplying R1 plus R2 is equal to R1 times IT, the total current. Then we divide by R1, then we divide by R1. Remember, we said R1 and R2 are the 9.33 ohm and the 8 ohms respectively. They are our R1 and our R2 in this scenario. Please do not be confused. I am not using I'm just taking the formula, the current divider formula. It's not these R1 and R2 we have in the circuit already. No, they are not the ones I'm referring to. I'm referring to the effective resistance of this branch. So if it is a bit confusing for you that I'm using R1 and R2, we can use RA and RB just to show that they are not really the same resistances we have on our circuit as it stands right now, right? So I am saying our formula there, making IT the subject, means now it's equal to IT is equal to I2 multiplying R1 plus R2 over R1. bear in mind, we are saying it's not the R1 and the R2 already indicated on the diagram. No, we are saying according to the use of the current divider rule. According to the use of the current divider rule. Right. So we are saying this is what we now have. I2, we have it already, that's 0.3. Multiplied by, remember, our R1 and R2, they are the 9.333 plus 8. They are the ones we are labeling, we are indicating as R1 and R2 in this case. Divide by 9.33. You realize that you arrive directly at the same answer, the 0.557 amperes. So there are many ways of killing a cat. There are many ways of arriving at the answer. So you realize it's not much that the question there is really asking. Right. So the total voltage of the circuit. So the question is now asking the total voltage of the circuit. Right. Total voltage, now we have total current. VT is equal to I total multiplied by R total, the total resistance. So we can just take the total current directly, 0.557 that we already have. 0.557 multiply the total current that we calculate, 27.308. So if we multiply, we end up having 15.211 volts. That marks our total voltage of the circuit. Then lastly, there was a question which was saying the power dissipated on R1. Right? So R1 is dissipating the power of what? We can just say power is equal to V times I. True, we can say that where V is the voltage of the 8 ohm. Or we can just go straight and say power is equal to I squared multiplied by R, considering that what we have already is the current which is passing through the 8 ohm. What is it? It is the total current. That's the current which is passing through the 8 ohm before it is subdivided here at this junction. Right. So we can just use that total current 0.557 squared multiplied by the resistance of the resistor R1, which is 8. Right. So we did calculate that. And if we punch that on the calculator, what is it going to give us? It's going to give us 2.482 watts. Power is measured in watts. That's our power there. Right. So basically, this is what is happening. Let's quickly go to question number 3. Right. Question number 3. Right. We've been given the phasor diagram there, and we are being told if the system above has a supply voltage of 240 volts, 50 hertz, calculate the value of the inductor in millihenries. So that's the first question, right? We have been given XL, which is the inductive reactance. And the question is now asking us the inductance. So we retrace our steps. How in the first place do we calculate inductive reactance? Inductive reactance is given by 2 pi FL. So let's make inductance the subject. Divide by 2 pi F both sides. Divide by 2 pi F this side. Right. It means L is equals to XL over 2 pi F. Right. So we can just substitute what we are having directly into the formula. Right. What do we have? We have the inductive reactance 38 divided by 2 pi multiplied by frequency. We have been given the frequency there in hertz. So we simply substitute it as well, 2 pi multiplied by 50, right? So we can punch that directly on our calculators. 38 divided by 2 pi times 50. We get the value 0.121. That's the value we are going to get on the calculator. Then you just press the E and G button. There is a button written E and G on the calculator. If you press it, this button here, if you press it, it will give you your answer as 120. Why? Because the instruction is saying in millihenries. So since you want your answer in millihenries, it's times 10 to the power of -3. So if you just press that button once, it gives you the answer as 120. So it has already been called 120.958 etc. So to 3 decimal places, it becomes like times 10 to the power of -3. That's what you are seeing there on the screen, which means that 10 to the power of -3 is the millihenries that we want. So therefore, our answer is 120 0.958 millihenries. That's our answer there, right? So we are using our calculator. It makes it quite easier. Farads, the value of the capacitor in microfarads. So for the capacitance now, what are we going to do? Again, we retrace our steps. Look what we've been given. We had been given the capacitive reactance, XC. So retrace, how do we in the first place calculate that capacitive reactance? We calculate it using the formula XC is equal to 1 over 2 pi FC, right? So let's make C the subject. Multiply by 2 pi FC, multiply by 2 pi FC on both sides. It means 2 pi FC XC is equal to 1. Then what do we do? Divide by 2 pi FXC. Divide by 2 pi FX 2 pi FXC, making C the subject. So these, they cancel each other. We are left with C is equal to, we've made C the subject there. So C is going to be equal to 1 over 2 pi multiply by FXC, right? So hence it becomes possible now to find C, making it substituting the values that we have, 2 pi multiplied by f, the frequency, which is 50, multiplied by xc, which we have been given 31.8, right? That's what we are having. So we can now punch that directly on the calculator, right? If we punch this on the calculator, we are going to get a value 10 something 0097. It's actually 1,00957 times 97 times 10 to the power of -4. That's what we are seeing on the screen of our calculator, right? We go again and punch just once. You just punch the button E and G on your calculator there. Yeah, if you're using the Casio, right? It's the engineering bit button that you are punching there, right? You are changing. So I'm using the Casio calculator to try and explain that you can actually do it, because I know it's the most common one that we are using. So you can actually just do it on your calculator directly. So you will get 100.097 times 10 to the power of -6. That's what we are seeing. Apparently, that's microfarad. So times 10 to the power of -6. That's our microfarad. So micro is 10 to the power of -6. So 100.097 microfarads. There we go. That marks our capacitance there. Okay, let's quickly go to the impedance in ohms. So we want to calculate the impedance now. We have XC, we have X, we also have R, the resistance. So it means it's possible to calculate, we can use directly Z is equal to the square root of R squared plus, we have XL and XC, so we will say XL minus XC bracket what? Squared. So we can just directly substitute what we have, the square root of 20 squared plus bracket XL 38 minus 31.8 squared. And what do we get? 20.939 ohms. Right, that marks our impedance there. Then the next question is the impedance, the supply current in amperes. The next question is saying calculate the supply current. So supply current IT is equal to V, the supply voltage, over Z, the impedance of the circuit. So we will say we've been given the supply voltage there is 250, the one that was given together with the frequency, divided by the impedance we've just calculated, 20.939. So together they are going to give us 11.939 if we punch that on the calculator. right? So basically, this is what is happening, 3.3, 3.4. Now we are on 3.5. Now on 3.5, the angle between, calculate the angle between the current and the voltage. Apparently, that's the phase angle that we are being asked to calculate. So in calculating the phase angle, we can use different formulas. We can say, considering the series circuit, we are saying theta is equals to arctan of XL minus XC, because already XL is greater than XC in this case, over R. We can say that. Or we can say theta is equals to arc cos of R over Z. Still, we are fine. Or we can say arc tan theta is equals to arc sine of XL minus XC over Z. We can still get the same answer. Okay, so I'm going to stick to this one directly. Arc tan of 38 minus 31.8 over 20. Right. That's what we've been given there. I would advise often when you have an option of using what is already there on the given information, when you are in the exam, use that, because sometimes your own values that you would have calculated, you might have slightly made a mistake along the way. You see, it happens. To err is human. So I'm saying trust using the information. If ever you have a choice or you have an option, use the information that you have already been given. So we end up having 17.223 degrees. Okay. So I'm not necessarily encouraging making errors, because it's costly in the exam. Do not do that. Okay, 3.6. 3.6, the question is now saying calculate the voltage. Okay, we are now calculating the voltage of the voltage drop across the inductor and the capacitor. And I'll just try to clear my screen then. Okay, so the voltage drop across the inductor and the capacitor. So we start with the voltage across the inductor first. VL, let's call it that. VL is going to be given by the series circuit. So it's going to be given by IT, the supply current, multiply by XL, the inductive reactance. So we take the supply current, the total current of the circuit, 11.939 that we have calculated there, multiply it by 38. And that will give us 453.682 volts. Then VC, calculate VC. It's going to be IT again, multiply by XC. So 11.939 multiplied by 31.8. And that will give us, that's going to give us 379.660 volts. That marks the VC. Okay, so we go to question number 4. Right, question number 4 is saying, define the term semiconductor. So semiconductor, we can define it as a material that is neither a good conductor nor a bad insulator. It's in between. Or a semiconductor is a tetravalent material. By that, we are saying it is 4 valence electrons. That's a semiconductor. Often knowing that an insulator has 8 valence and a conductor has less than 3 valence electrons. Okay, so we can actually define it also in that way. So let's go to 4.2. Draw a fully labeled half-wave rectifier circuit using a transformer, a diode, and a smoothing capacitor, and a load resistor. So let's try to draw that here. Right, this is how it looks like. Right, we have a supply here. We can indicate the supply voltage, the AC supply. Right, then we have the primary side of our transformer. So I'm going to indicate it here. This is marking the primary side of the transformer. Right, and this is the symbol for the transformer, showing oftenly the air gap that is in between. Okay, then we have the secondary side of the transformer. Right, we indicate the secondary side of the transformer. Right, we indicate this point is positive A here. We label it as A. Then we indicate the diode. Right, then marks our diode. Right, remember we have one diode. I indicate again the other point. That's negative B there. That's another point again. Right, and then we have our capacitor. It's connected in parallel. It's a smoothing capacitor or a filtering capacitor. That's the purpose it is serving there, for filtering the AC harmonics or the AC signals that would not have that would have remained after the rectification. Okay, so then we have the load resistor, we have the resistance, the load resistor there at the end that marks our load resistor there. It is in parallel with the capacitor. In parallel with the capacitor, there is our, so we can label them now. We can label this as C or as C1. Then we have this as RL, right? This, and then we have this as our D1, right? And of course, this point we are labeling it A, we are labeling this one B. We can label the secondary side of the transformer VS, the primary side we label it VP. That's our AC input. That's our input here, right? So that marks our capacitor. As a matter of fact, this is a half-wave rectification circuit with a filter circuit. So the capacitor there is acting as a simple capacitor filter circuit. That's a filter circuit there. Explanation, they say, explain the operation of the half-wave circuit drawn in question 4.2. Explain the operation of the half-wave circuit diagram. So I want to explain how does that circuit operates, right? So you are to indicate this, that during the positive half cycle, when A, this point here, is positive with respect to B, diode D1, our diode, is forward biased and current flows, charging the capacitor to VM, the supply voltage, VM, right? That's your first point. Then you can now say, during the negative half cycle, when point B is now positive with respect to point A, diode D1 is reverse biased. It's reverse biased, therefore, the supply is effectively disconnected from the load due to that. And the capacitor is the only source of the voltage. The capacitor now discharges its charge into the load, the charge that it has accumulated during the positive half cycle, right? This is your second point. Then the presence of the capacitor changes the conditions under which the rectifier diodes conduct. When the voltage increases during the positive half cycle of the supply voltage, the capacitor charges to the peak of the input voltage wave, VM. That's the explanation. That is the operation of the half-wave rectifier circuit with the smoothing capacity form. 4.4 is saying a transistor can be used as an amplifier, the operating principles of the amplification. So here we need the diagram as well as the principle of operation of that particular diagram, right? So this is what we need. This is the diagram that we use to explain the amplification, right? We have the resistor here, resistor R1, and we have another resistor here, known as resistor RV, right? It's here. Then there is our transistor, right? Starting, okay, it's a little bit, my diagram there is a little bit, okay, let me try to indicate it nicely. Right, so, okay, there we are. Right, okay. Then we go towards, okay, there we are. That's our diagram. Then we have a lamp right at this point. Okay, there's the lamp. Okay, that's a light there. indicating that it's light, it's a light, we can indicate using this, right? And then, of course, the transistor, that's an NPN transistor now. The arrow is pointing out. There is the arrow of the NPN transistor, right? Then we have our supply. We have a battery connected. We can indicate the battery now. Okay. Then we have the battery. We have our battery there, right? Then we have that marks our circuit there. Okay, there we go. That's, so let's label it. This is a lamp. We indicate it as a lamp. This is our transistor. We indicate it as Q1. This is RV. Then this is R1. That's our circuit there. Right. And then the operation of this circuit, we need to explain again. So we'll say if the circuit is switched on, current will flow in the base of the transistor via R1 and RV. The transistor would switch on and the small base current would cause a larger current to flow in the collector circuit. As a result, the lamp would glow, right? And now, if the resistance of the variable resistor R1 were increased, RV were increased, the base current would decrease, causing the collector current to decrease and the lamp would dim. If the resistance of the variable resistor were decreased, the base current and the collector current would increase, causing the lamp to glow brighter. That's the explanation needed, which is marks the operation of our circuit there. Let's quickly go to 4.5. So we have 4.5. Refer to the circuit diagram below and explain the operation of the transistor used as a switch. As a matter of fact, this is the circuit diagram. This is the diagram of the operation of the transistor as a switch. The operation of the transistor as a switch. Right. So in explaining, right, this is C, by the way, this is a C here. So you say in the explanation, when conductor C, this conductor that we see here, is connected to point A, current will flow into the base circuit and the collector would flow, causing the lamp to glow, right? In this position, the transistor is fully on. It means it's at saturation. That's when C is connected to A, right? Now, when contact C is at point B, is connected at point B, no current would flow because the transistor is reverse biased. In this position, the transistor is off, which means it's a cut-off region, and the lamp is off. So this explanation, just like that's the explanation that is needed. By the way, I just want to add something that this explanation that you are seeing is explaining also the characteristics. Remember, the characteristics of the transistor best explains how the transistor operates as a switch. That we have the cutoff, with the active region, we have the saturation region, right? That's what we are referring to there, right? So it's important to co-join that information. That's the transistor as a switch, that's the transistor as an amplifier. Okay, let's go to the next question, question number 5. Right, question number 5 is saying, 5.1.1. The electronic network has an output voltage of 240 volts and an input voltage of 120 volts. The input and the output impedance is 600 ohms. Calculate 5.1.1, the input and the output power of the system, right? What do you consider? You consider the information that you have been given. What have you been given? You've been given output voltage and input voltage. You've been given input and output impedances as well. So we can calculate P out. Let's start with P in. We can calculate P in by saying V in squared over R in because of the information that we have. Right, so we have V in, apparently, that's 120 squared, divided by R in, that's 600 there. Right, if we punch that, that's going to give us 24 watts. That's kind of straightforward there. Let's go to V out, to P out. P out So this is decibels, by the way, where this is being borrowed from. P out is equal to V out squared over R out, right? The output impedance. So what is it? 240 squared divided by 600 as well. What do we get? That's 96 watts if we punch that nicely on the calculator, right? So we have calculated the input and the output power. We have them. Let's go to the power gain or loss of the system, right? Power, AP, this is gain, is equal to 10 log P out over P in. That's the formula we use there to calculate the power gain, right? So 10 times log, what is our P out? That's 96. Divided what is our P in? That's 26. So as a matter of fact, that's what, remember, our gain or loss. It is the ratio between the output and the input. So of course, it has to be measured in decibels. So that's why we are now using the logarithms there, right? So if we punch that on the calculator, it's going to give us 6.021 decibels. Then there follows our next question, which is saying, define the term decibel. So decibel is simply a 1/10 of a bell, or it's 10 decibels is equal to 1 bell. That's the definition we give of a decibel. Deci means from the decibels, or it's 10. That's what it simply means, okay? So decibel is 1/10 of a bell. Right, let's go to 5.3. Explain the operation of the following transducers. A thermocouple. Right, we want to explain how a thermocouple operates as a matter of fact. A thermocouple, it's a temperature-sensitive device, just like also the bimetal strip there. So we simply say that when the temperature differences exist between the hot junction and the cold junction, of the potential difference, the potential difference is produced that causes the current to flow, right? And when a meter is connected to the terminals of the cold junction, the meter indication will be proportional to the difference in temperature between the hot and the cold junction, right? So that's the explanation, the operation actually of the thermocouple. Just to add on to that explanation, that operation that we've been given, I just want to explain the thermocouple here a little. It's just out of context, out of interest. I just want to explain that. So this is the circuit diagram actually of the construction of the thermocouple, how it's constructed. So I need us to know that what happens is that it is, as I have said, it is a sensitive temperature device. It's a temperature sensitive device. So it is made up of two metal alloys. So you see metal A, the metal B, for example, mostly is nickel chrome, and the other one can be nickel aluminum. So metal A and metal B that you are seeing there. Then the conductors are typically built into a cable that is having a heat resistance sheath. Right, and then at one end of the cable, the two conductors are electrically shorted together, right? And this end of the thermocouple cord is the end which is called the hot junction, which is this part that you see here, the one that I'm trying to indicate here. So it is the one we are calling the hot junction, and also known as the sensing junction. And it is thermally attached actually to the object to be measured. That's how it is. So I just wanted to add this fact, which helps also to understand how the thermocouple really looks like. Let's just go to the next question. The next question, they say the bimetal strip. The bimetal strip. So just like it as well, the bimetal strip is made up of two metals as well. Often it's copper and it's aluminum. I'll just quickly try to indicate them here. So it's usually like this. One is copper and the other one is aluminum. So this is the copper strip. This will be copper, and the other one will be what? That will be copper there, and the other one will be iron. The other one will be iron. That's how it is, right? So basically, this is what is happening. That's how it is. Then the other one, there is iron, there is no iron, right? Let's explain the operation of the bimetal strip. So again, it's a temperature sensitive device. Now, when the bimetal strip is heated, each metal, by the way, the question didn't ask us to draw. I'm just explaining, but when you are asked the operation, you just explain the operation and they don't draw the diagrams. It's not necessary. I'm just doing that so that I put more emphasis in explanation so that we can understand really what is happening. So we are saying when the bimetal strip is heated, each metal begins to expand at its own rate of expansion. So e.g. copper and iron that we're having there. Copper has a larger coefficient of expansion, so the strip of copper layer expands faster than the iron strip and also shrinks faster than the iron. So by so doing, that's the explanation of the operation of the bimetal strip. And this is how it actually looks like. So it means that the one that is going to expand faster, it results in the metal bending towards that. Right? So that's what normally happens. Right? Let's quickly go to question number 6, the next question. Right? A moving coil meter has a full-scale deflection of 4 milliamperes and an internal resistance of 50 ohms. Calculate the value of the shunt resistor that would enable the meter to measure a current of 4 amperes. Right? I want to explain this question, accompanying it with a diagram. With a diagram that I want, right? The diagram of the shunting connection that has been done. There is our meter. It's indicated as M, right? And then we have our resistor. There is our resistor there. There is our resistor there. Okay. That's our shunt for us. Right. There is I shunting. There is, of course, there is IM. There is IM, and we have RIM, of course, the resistance of the meter. Then we have I, the current that is coming from the supply, right? When we are calculating here R shunt, it's simply coming from a formula that we know. The voltage of the shunt resistor apparently is also the voltage of the meter. V shunt is equal to VMY because they are in parallel. Hence, for that reason, I shunt times R shunt, which is V shunt, is equal to IM multiplied by RIM. Right? So, if we make R shunt the subject, R shunt is equals to IM RM over I shunt. But do we have I shunt? No, we do not have it. What we've been given there, the full scale deflection, 4 millimeters, 4 milliamperes, it has to measure. How are we going to calculate I shunt? We use this junction here. This is the junction that we use this one. So we use Kirchhoff's first law. Current entering the junction is equal to current leaving the junction. I is equal to IM plus I shunt. That's what is happening. So making I shunt the subject, because it is the one that we want for this formula here that we've created, is equal to I minus IM. So henceforth, we can say 4 minus 4 times 10 to the power of what? Of negative 3. Why negative 3 milliamperes? So that will give us, that's our I shunt there. Right, so we can now come and substitute into the formula. We have everything. Now, IM, we already have it, is 4 times 10 to the power of negative 3 multiplied by RIM, that's 50 there, right? Over 4 minus 4 times 10 to the power of negative 3, which is 3.996, right? And R shunt can now be determined as 0.05 ohms. That's how we calculate it. Right, let's quickly go to the other question here. The other question is saying, give 5 advantages of digital multimeters. So there are plenty of advantages that actually a digital multimeter has. Among them, it is accuracy is high, it is more robust, which means it's more stronger, and it is much more sensitive. An error of parallax, looking at an end, is eliminated. It's called the error of parallax. Then can handle negative quantities. And reverse polarity is indicated by means of an indicator on the display, right? These are some of the advantages that it actually possesses. Let's go to the last question. They say, draw a labeled circuit diagram of a synchro system to illustrate how a 180-degree phase shift coupling between the transistor and receiver is achieved, right? So I'm just going to draw the diagram here quickly. Okay, so here is how it looks. Okay, we can draw it in this way. Okay, there it is. Right. Okay. This is the part that I want to start it. Still fine. Okay. There we are. Right. Let me try to draw it nicely. Okay. There we are. Straight line here. Right. And this one goes up. Okay. This one goes up as well. Right. And then we have the other side. There is an interconnection here with another resistor as well. Right. And then it goes okay. Interconnect with another. Oh, right, there it is. Again, another resistor here. Then it's connected again. There we are. Okay, and then it's directly connected now. There we are. This is how it. Okay. Okay, this is the part where we are at. Okay. Here. So it's connected directly. We have it is connected to this other part. Okay. Right. So and then we have another S1 again here. Okay, and then it's interconnected directly. There we are. There we are. Right. Okay. So then we have another resistor again at this point. We indicate it. Okay. There we have it. There is another one. Right, and then we have a supply right here. There is our supply. It's connected. There is our supply. So it's an AC supply, a single phase AC supply. Of course, just want to straight. Okay, there it is. There's my diagram there. Pardon me, my diagram is a little bit poor, but I'm trying to bring out what we have here on the synchronous. Right, and then we have AC supply. There is an AC supply. Right, it's a single phase there. And then interconnected again to the other one. There we have it. There it is. Okay, and then there is the other one again. Okay, there it is. There is a connection again here, directly connected to this. Right, so let's quickly label it. We have R1 here. We have R2 here. And we have S2 at this point. We have S1 here, and still have R1, R2 here, and we have S3 at this point. Right. There is marking S3. Right, that's S3 there. That's also S3 here at this point. Right, and there is S1 actually is at this point, and that's S3 there. Okay, so this is a S3, now S3 here, and this marking S3. By the way, this is marking S2. This is S1, which is also interconnected to S1 here. Right, there is our diagram marking. This is the receiver, and this is the transmitter. Right, that's how it is. So we are saying that's how our diagram looks like. S2 connected to S2 there, S1 to S1, S3 to S3. So it's marking a 180 phase shift between the transmitter. That's how it has to with the 180 phase displacement. So this apparently marks the end of the revision of our paper, and that's the end we're having there. Okay, thank you.